Yes, we expect James Webb to make great discoveries. We expect that.
Hello, space enthusiasts and curious minds. Welcome back to our channel, where we dive into the wonders of the cosmos. Absolutely, there's a buzz around James W's potential for remarkable breakthroughs. Let's turn back the clock to 2021, when NASA, the global leader in space exploration, triumphantly launched one of the most sophisticated space observatories ever constructed. This monumental achievement was the result of a global partnership involving not just the Americans, but also the European Space Agency and the Canadian Space Agency. However, within just a year of its launch, this state-of-the-art telescope faced an unexpected challenge. Its delicate golden mirrors were struck by an enigmatic object, potentially endangering the telescope, worth over $1 billion, with irreversible harm. But why would we send a telescope with unprotected mirrors into the vastness of space? What was the nature of this enigmatic object, and where did it originate? These questions raise concerns about the foresight of NASA's engineers regarding space debris. Is the James Webb Space Telescope permanently impaired? Join us in this intriguing video as we delve into the mystery surrounding the collision with the James Webb Space Telescope. We'll explore the complexities of space debris and other unanticipated challenges that this pioneering telescope has encountered. Known as the James Webb Telescope, this marvel of space technology story is one of innovation, challenge, and exploration. The James Webb Space Telescope, JWST, initially envisioned in 1996, was originally named the Next Generation Space Telescope. By 1999, two designs were in progress, aiming for a 2007 launch with a budget of $1 billion. However, the project encountered significant cost overruns and delays, leading to a final redesign in 2005. The JWST's primary mission is to capture light from the universe's earliest stars and galaxies formed post-Big Bang. Additionally, it's tasked with investigating galaxy formation, the evolution of stars and planets, and probing the origins of life in planetary systems. In 2002, the project was renamed in honor of James Webb, a key figure in aerospace engineering and space exploration, and the second administrator of NASA. Serving for 7 years, Webb's visionary leadership was crucial during a pivotal era in space exploration, helping the United States gain a significant position in this field. Webb, who earned a Bachelor of Arts in Education in 1928, also had a background in law and public service. During Franklin D. Roosevelt's presidency, he held various roles, including an associate position at the Sperry Gyroscope Company and legal responsibilities. Webb's influence and contributions significantly shaped the JWST project and its objectives in exploring the depths of space. James Webb, after being appointed NASA Administrator in 1961 by President John F. Kennedy, played a pivotal role in steering America through the heated Cold War space race against the Soviet Union. He was instrumental in overseeing the iconic Apollo program, which culminated in astronauts Neil Armstrong and Buzz Aldrin landing on the moon in 1969. Under Webb's leadership, NASA initiated groundbreaking endeavors, including the Gemini and Mercury programs, which set the stage for more complex space missions. His vision extended beyond Earth as he led missions to Mars and Venus. Webb's tenure at NASA was also marked by a commitment to diversity and inclusivity, significantly increasing the participation of women and underrepresented groups within the agency. His transcendent leadership earned him numerous accolades and solidified his legacy in the annals of American space exploration. Even after his passing in 1992, Webb's influence on global space endeavors persisted. A testament to his impact is the advanced telescope named in his honor, the James Webb Space Telescope, which is poised to revolutionize our understanding of the cosmos for many years to come. The James Webb Space Telescope, completed in 2016, is an advanced observatory equipped with infrared technology for space observations. It boasts high resolution and sensitivity, surpassing the capabilities of earlier telescopes like the Hubble Space Telescope. While Hubble remains operational, the James Webb Telescope excels in observing older and more distant celestial objects. This telescope plays a crucial role in various fields such as astronomy and cosmology, allowing us to study the universe's earliest stars and the formation of the first galaxies. It is also adept at conducting detailed analyses of the atmospheres of potentially habitable exoplanets. After extensive testing, overcoming budget escalations to $10 billion, and facing delays due to the COVID-19 pandemic, the James Webb Space Telescope was launched on December 25, 2021, from Kourou, French Guiana. It reached its operational position in solar orbit near the Sun, Earth L2 point in January 2022, located approximately 930,000 kilometers from Earth. The telescope's first image was unveiled in July 2022. The James Webb Space Telescope is distinguished by its unique shape and design. Its innovative structure and capabilities mark a significant leap forward in our quest to understand the vastness of space. The James Webb Space Telescope's primary mirror is an engineering marvel composed of 18 hexagonal segments made of gold-plated beryllium. Together, these segments form a 21-foot mirror, significantly larger and more effective than the Hubble Space Telescope's 7-foot mirror. This design gives Webb about 6 times the light collecting area of Hubble. While Hubble observes in the ultraviolet, visible, and near-infrared spectra, Webb is designed to observe a lower frequency range, spanning from long wavelength visible light through the mid-infrared spectrum. Due to its extraordinary sensitivity to infrared light, Webb needs to operate at very cold temperatures, specifically below 370 F. To maintain this, Webb is equipped with a 5-layer sunshield, each layer as thin as human hair. Made of Captain E film coated with aluminum on both sides and a layer of doped silicon. This shield effectively reflects the sun's heat, thus preserving the telescope's sensitive instruments at the necessary low temperatures. Webb also boasts a more advanced and faster onboard computer than Hubble. Specifically designed for near-infrared astronomy, Webb can observe visible light only in the orange and red spectrum, as well as the mid-infrared region, allowing it to detect and analyze a range of celestial phenomena previously inaccessible to astronomers. The James Webb Space Telescope is capable of detecting objects 100 times fainter than those observable by the Hubble telescope or ground-based telescopes. While ground-based observatories have been instrumental in discovering comets and planets, they face limitations in visibility and scope. One major drawback is their need to peer through Earth's atmosphere, which, despite appearing transparent, contains many chemical compounds that complicate astronomical observations. In contrast, the Webb telescope can observe objects within the solar system at angles greater than 85 from the Sun. It is also equipped to rapidly respond to unplanned cosmic events, such as supernovae and gamma-ray bursts, often within 48 hours of detection. Beyond its external features, the Webb telescope is outfitted with sophisticated technology. Its integrated science instrument module provides crucial electrical power, computing, and cooling capabilities. The near-infrared camera, equipped with 10 sensors each of 4 megapixels, precisely aligns and focuses the main mirror segments. The near-infrared spectrograph, a complex array of spectroscopy equipment, enables robust observation across multiple criteria. In an intriguing development in May 2022, the James Webb Space Telescope. In an unexpected turn of events, the James Webb Space Telescope was struck by a significantly large micrometeoroid. NASA reported this incident in June, noting that the size of the debris exceeded the parameters anticipated in pre-launch models. Images released by the project's scientists illustrated the extent of the damage inflicted on the telescope's mirrors. The performance of Webb's primary mirror, which is crucial for interpreting incoming starlight, was compromised by the impact. The collision increased the error associated with the entire main mirror to about 59 nanometers root mean square. Engineers had anticipated the spacecraft being hit roughly once a month by micrometeoroids of negligible sizes, a factor that was incorporated into its design. Despite this incident, the report indicated that the overall effect on Webb remains minimal. However, scientists are still evaluating the long-term consequences of these micrometeoroid strikes on the telescope. Designed for a minimum operational lifespan of 20 years in space, the impact of this event on the longevity and functionality of this multi-billion-dollar endeavor remains uncertain. Micrometeoroids are minute particles of dust and debris orbiting the Sun, typically ranging in size from 50 microns to 1 millimeter. In space, these small but potentially impactful particles, due to their small size, micrometeoroids travel at speeds significantly faster than typical meteoroids, making them capable of causing substantial damage, akin to high-velocity bullets. These tiny space particles originate from various sources, including comets, asteroid collisions, and other cosmic events, and they represent a constant hazard to spacecraft. Micrometeoroids are a well-acknowledged risk in space operations, known for causing notable damages to significant space endeavors like the International Space Station and the Hubble Space Telescope. Interestingly, only about 10% of micrometeoroids are associated with meteor showers such as the Perseids and Leonids. The remaining 90% are sporadic, traveling alone on random orbits, which makes them incredibly difficult to detect from Earth. The impact of a micrometeoroid on a spacecraft depends on its mass and velocity. While these particles generally pose no threat to Earth, burning up in the atmosphere as shooting stars, before reaching the ground, spacecraft lack this protective atmospheric shield, making them more vulnerable to collisions. Over time, consistent impacts from these space particles can lead to the erosion or puncturing of spacecraft surfaces, posing challenges for long-term space missions. The exact population of micrometeoroids in cislunar space, the region encompassing the Earth and the Moon, remains a mystery, largely due to the variability of conditions in space. For instance, a higher density of these particles is often found in the ecliptic plane, where most of the solar system's dust is concentrated. The size of micrometeoroids can also vary, influenced by factors such as the spacecraft's orientation and levels of solar activity. Space agencies around the world are actively engaged in comprehensive studies of the micrometeoroid environment. These efforts involve ground-based testing, modeling, and direct measurements. Using data from satellites like SLAS and the Long Duration Exposure Facility, scientists are able to simulate the potential impacts of micrometeoroids on various materials. One method for this simulation is the use of hypervelocity guns to replicate the damage these particles can inflict on spacecraft. To protect against micrometeoroid damage, many spacecraft are designed with specialized shielding. One notable example is the Whipple shield, first proposed in the 1940s. This shield consists of layered plates designed to disintegrate incoming particles. Modern versions of this shield often incorporate a combination of Nextel fabric and Kevlar layers. Kevlar, known for its use in bulletproof vests on Earth, provides robust protection against the high-speed impact of micrometeoroids in space. Various spacecraft employed different strategies to mitigate the risk of micrometeoroid collisions, including the use of glass panels, protective blankets, and strategically positioning sensitive components like radiators. The level of threat posed by micrometeoroids varies depending on the spacecraft's operational region in space. For example, the risk is significantly lower in low Earth orbit compared to interplanetary space. Given that the James Webb Space Telescope operates at the L2 point, scientists had anticipated the likelihood of occasional unavoidable impacts over its operational lifespan. These potential impacts were factored into the telescope's design. Nonetheless, consistent micrometeoroid strikes continue to be a challenge that scientists must navigate. The Webb Telescope's location offers a more stable operational environment compared to the Hubble Space Telescope's low Earth orbit, facilitating extremely precise imaging without terrestrial disruptions. Unlike Hubble, which was designed to be serviced by astronauts, the Webb telescope is positioned too far from Earth for direct human intervention. This remoteness necessitates flawless deployment, as there's no margin for error in its operations. Following the micrometeoroid strike, the team assessed the telescope and found it to still be functioning at its highest capacity, maintaining. The James Webb Space Telescope has not only met, but exceeded all mission requirements, demonstrating its robustness. Scientists subjected the observatory to various tests to ensure its readiness for operations in orbit. However, the impact it sustained in space was more significant than what the team had originally modeled and tested on the ground, leading to concerns among some scientists. In response to this unexpected impact, NASA has taken measures to safeguard the Webb telescope from potential threats like ultraviolet light and cosmic rays in the galaxy. The technical deputy project manager at NASA's Spaceflight Center in Maryland emphasized that Webb is equipped with optical, thermal, electrical, and mechanical performance margins to cope with such challenges. One reassuring feature of the James Webb Telescope is its ability to sense and adjust the positioning of its mirrors, allowing for partial correction of the effects of impacts. By fine-tuning the position of the affected segment, engineers can mitigate a portion of the distortion, thus minimizing the impact on the quality of the images it produces. Engineers have already initiated the first adjustment for the affected segment, known as E3, and will continue these adjustments until they achieve the desired level of correction. Throughout its mission, the James Webb Flight Team has the capability to employ protective maneuvers to redirect its optics away from potential threats, such as known meteor showers, before any damage can occur to the telescope's mirrors. While the recent micrometeoroid strike was considered unavoidable, space experiences fairly frequent instances of meteor showers that may pose some risk to the telescope. Lee Feinberg, the Webb Optical Telescope Element Manager, has noted that the impact of micrometeoroids could potentially degrade the telescope's performance over time, primarily because Webb's mirrors are exposed to the harsh conditions of space. Feinberg also disclosed that there have been 14 smaller but measurable micrometeoroid strikes, aligning with the expectations for the telescope. Using the data gathered from this recent strike, the Webb team plans to update their analysis and develop operational approaches to ensure the telescope's imaging performance remains at its highest level. Beyond the challenges posed by micrometeoroid strikes, the James Webb Space Telescope has proven immensely valuable in enhancing our understanding of the cosmos. In July 2022, ENASA released the first full-color scientific images from the telescope, marking a significant milestone in our quest to comprehend the world around us. The release of the first full-color scientific images from the James Webb Space Telescope sparked tremendous excitement within the astronomy community. This momentous occasion signified another significant stride in our ongoing quest to unravel the mysteries of outer space. The released images included the deepest and sharpest infrared image of the distant universe ever captured. This breathtaking deep field image, assembled by Webb, provided a captivating glimpse into the past, spanning over 13 billion years to witness the formation of galaxies shortly after the Big Bang. In this awe-inspiring snapshot, one can observe swirling spiral galaxies, massive elliptical galaxies, and bright star clusters. The telescope's capabilities extended beyond distant galaxies to unveil striking details of our neighboring planets. Infrared imagery offered previously unseen views of Neptune, Jupiter, and Mars. Notable observations included the extension of auroras to high altitudes above Jupiter's poles, and the delicate ring structures encircling the planet. Additionally, the icy Neptune shone brightly with its clear methane clouds, while Mars emitted distinctive streaks of photons. These remarkable observations have sent scientists into a whirlwind of conjecture and exploration. Notably, the faint rings of Neptune, first glimpsed during the Voyager 2 flyby in 1989, have once again captured scientific attention. Situated 30 times farther from the Sun than Earth, Neptune appears darker overall, a characteristic attributed to its high-altitude methane ice clouds. The insights gained from these observations have ignited a fervor of scientific inquiry and discovery. The James Webb Space Telescope also delivered high-quality views of the Carina Nebula's stellar nursery, located on the edge of a vast gaseous cavity approximately 7,600 light-years away. The imagery revealed a multitude of previously concealed stars and numerous distant galaxies that had eluded detection by older telescopes. One of the stars captured within the Carina Nebula had first been catalogued by James Dunlop in 1826, visible from the southern hemisphere. This image offers invaluable insights into the earliest phases of stellar life cycles, shedding light on the intricate processes of star formation. Welcome to Blisovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blisovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q and a sessions with experts. Your membership will grant you the chance to participate in Live Q and a sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blisovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.